To lecture number 84. We are studying transient analysis, and in this lecture we will continue solving an example we started in last lecture, CA83. Right. The example circuit contains a switch along with a capacitor, 3 resistors and 2 voltage sources. The switch remained open for a very long time unless the circuit achieved steady state. This means that this capacitor was fully charged at a voltage we calculated in last lecture, and then it was moved to position. It was closed, replacing this branch with a short circuit, and we were asked to find out I of t and V across capacitor V sub C of t for all t. In last lecture, we solved half of this problem. We computed V sub C, the voltage across capacitor at 0 minus. This means just before closing the switch at 0 plus. And it was the same. Why? Because the voltage across capacitor cannot change all of a sudden. I at 0 minus, I at 0 plus, I at infinity, and V sub C of infinity were also calculated by us in CA83. In this lecture, we will compute V sub C and I as a function of time for all t, and we'll complete this problem, or we'll complete this solution. Right. To do that, we have to draw this circuit, and this capacitor is written as 100 microfarad capacitor charged initially at 32 volts, and this branch is replaced with a short circuit because now the switch is closed. So in order to find V sub C of t, the voltage drop across capacitor, whose initial value is 32 volts just after closing the switch, but we know that this 32 volts, the value 32 volt, is not retained. It decreases as the switch is closed, because the dynamics of the circuit or the topology of the circuit has been changed. So we have to compute this Vc of t, V1, and this V2. Surprisingly, this V2 is directly connected to ground, making our life easier because V2 is 0 then. So V2 can be safely written equal to 0 because it is directly connected to ground. And for V1, we will write the KCL equation, Kirchhoff's current law equation, assuming all currents are moving away from that node. And we'll write all the currents moving away from the node as positive values. So V1 minus 36 divided by 2K, and we know that current through this capacitor would be C times d by dt of the voltage. I is equal to C dV by dt, plus V1 over 6K is the current flowing in this branch, and I have written 0 instead of V2 because V2 is directly connected to ground. Solving this gives us d by dt of V1 plus V1 over 150 milli is equal to 9 over 50 milli. Since V1 is the same as V sub C of t, therefore we can replace V1 with V sub C of t, and then that will be a first order differential equation with some constant on the right hand side. For such equations, the general solution is k1 plus k2 e to the minus t over tau. Putting the initial value t is equal to 0 gives us the sum of k1 plus k2 is equal to 32. Putting the final value t is equal to infinity gives us k1 equal to 27, and then k2 can be computed as 5 using these two equations, and then Vc of t can be written as 27 plus 5 e to the minus t over tau. So the final thing we have to compute is this tau. So putting this Vc of t in this equation A, gives us gives us tau is equal to 0.15. And then we can complete this equation Vc of t, putting tau is equal to 0.15. So this gives us 27 plus 5 e to the minus t over 0.15 volts. How can we draw that? Putting t is equal to 0, this is replaced with a 1. So 27 plus 5 is 32. So the max value where time t is equal to 0 is 32 volts. And then it decreases. And what happens at time t is equal to infinity? T is equal to infinity, e to the minus infinity is a 0. So everything, so this much, sorry, this is for this expression, if we put t is equal to infinity, we are left with 27. So at time t is equal to infinity, this is 27, and this is the same we computed in last lecture. Vc at infinity was 27 volts computed by us using another way, right? So, and then I of t, if we know v sub c of t or v1, computing I of t is straightforward because this is grounded, this node is grounded. So this node is grounded. So the current would be v1 minus 0 divided by 6k, or v1 over 6k, or v sub c of t over 6k. So this is 6k, 6 kilo ohms. So this kilo, once taken to the numerator, becomes milli. So this is the value, this is the expression for I of t, and we can plot in the similar way that putting t is equal to 0 gives us a 1. This exponential becomes 1. So 9 plus 2 plus 5 over 6 is 16 divided by 3 milliamperes. And at time t is equal to infinity, this whole term becomes 0, and we are left with 9 by 2 milliamperes. So they both are decreasing exponentials, but none of these two values, Vc of none of these two quantities, V sub c of t and I of t, they reach to 0 as time approaches infinity. In fact, they both settle at a value larger than 0. This is because we have K1 and K2 different from each other. And in this case, we have K1 different from K2. So this is another kind of exponential for which the settling value at time t is equal to infinity isn't 0, and it is decreasing exponential. So that's all for this lecture, but at the end we have a homework. What is that homework? We have to draw these two quantities, V sub c of t and Vn and I of t in MS Excel. And should submit your work IAT in MS Excel, and should submit your MS Excel file as an assignment in MS Teams. So this is your homework. You have to draw these two quantities for different values of t. Which two quantities? V sub c of t and I of t. For different values of t, you have to try different values of t. You have to draw these two graphs in MS Excel, and you will have to submit that Excel file in MS Team in an assignment I'll create today. Thank you.